Hello, everyone, and welcome to this session. I'm very excited to talk to you about adding graphs to machine learning, which is a hot research topic today. And what I hope to show you is how you can use these technologies in Oracle Autonomous Database today. So here's the session flow. I'll start by discussing why it is interesting to look at adding graphs to machine learning applications. Then I'll give an overview of the graph data model. I'll follow that with some use cases which highlight exactly where there is a real value add when you add graphs to machine learning applications. And then I'll show you how you can use these technologies in Oracle Autonomous Database, and I'll finish up with some roadmap items that we have planned. So let me start with graphs and machine learning. So when you're developing a machine learning application, your goal is to look at existing data, create a model, and then use that model for predicting future events. So the classic example, of course, is in computer vision, where you would train your model using, let's say, pictures of cats. So when the system encounters a new picture of a cat, the system can correctly recognize that this is a cat. There are similar applications in character recognition, predicting customer behavior. For example, you might want to look at existing customer behavior to decide whether a new potential customer is likely to buy this product or not. And in all of these cases, you select the features you're going to use when you create your model and select the algorithm that you will use as you create your model. And machine learning, as we all know, has a variety of use cases. So if you're going to use Oracle machine learning, you have the choice of languages. And let's say you're going to be using SQL and PL SQL. Your code might probably look something like this. You're first building a model. You're selecting the algorithm to use. You're selecting the data to use, which is a list of features you want to use to create this model. And then you'll use this model to make predictions, whether this new customer is going to buy this particular product, let's say this insurance policy. So let's look a little more closely at what is happening here when we say using features in a model. So in this particular case, the features that were used for creating the model and for making predictions are things like the age of the person, the marital status, their bank balance, whether they own a home, and so on and so forth. So you take this information, you look at the information you have from other customers, you see based on this information, you make the connection whether this new customer is going to buy an insurance policy or not. But how about if we had additional pieces of information that would help you make a more accurate prediction? For example, is this person connected to other customers? Is this potential customer connected to other customers? And if these other customers are her friends, that might indicate some likelihood of whether she's going to buy this product because she's going to trust her friends more. So if you had a network of connections between her and other customers, and some of these network relationships were friends or colleagues and so on, that tells you something more about this customer and whether she's going to buy this product or not. And is she connected to customers who might not be her friends, but might be her friends' friends? Because she's likely to trust them more than she trusts complete strangers. So are there such connections between her and these other customers? And is she part of a cluster of people who have bought this product, this insurance policy? And this cluster of people are all people connected to each other by various relationships and perhaps tightly connected to each other. It could be a group of friends, could be a group of colleagues, or a group of people connected to each other by other relationships like the things they're interested in, the cars that they drive, and so on. So is she part of this cluster? Because if others in this cluster have bought this product, perhaps she is likely to buy this product. So looking at data, this potential customers, part of a network of relationships and connections is where graphs come in. Graphs enable you to identify the networks and run algorithms on your data when you view your data as a graph, so that you can get some insights into this customer's behavior based on the connections that are in this graph data model. So here, for example, is a simple graph where you have customers as vertices in the graph connected with other vertices by various relationships. So is she connected to a lot of buyers? That's a simple question you can ask by running a graph algorithm on a graph representation of your data. And that counts the number of edges connected to a particular vertex. So if she's connected to a lot of buyers, maybe she's likely to buy this product. That's the degree centrality algorithm. Another interesting algorithm, which is more nuanced, is the PageRank algorithm. She might not be connected to a lot of buyers, but she might be connected to another buyer who is connected to a lot of buyers. Or she might be connected to another vertex in the graph who is connected to a lot of buyers. So this kind of a this kind of relationship is identified by running the algorithm PageRank, which returns a numeric value between 0 and 1 for every vertex in the graph. So it helps you identify how connected this vertex is by not just looking at the number of edges connected to this vertex, but the connections that the vertices connected to this vertex have. So that's another algorithm that you can run on a graph to analyze the connections and networks in your graph. So the goal of adding machine learning, graphs to machine learning is to enhance the accuracy of the predictions of your model. So you have your raw data, that's the columns in red. And then you have additional features you can derive by viewing your data as a graph, and those are the columns in gray. So you can get numeric values for vertices in a graph by running algorithms like PageRank and degree centrality and other algorithms. And you can add them to this feature vector so that you're able to provide more information during the model creation process to have a better model, perhaps with more accurate predictions. So the goal of adding graphs to machine learning is to provide these connections in data to information that you're going to input to the model. And the model might have discovered these relationships by itself, the relationships between data entities. But if you're providing this data upfront to the model, that saves time when it comes to development of the model because there's more information available for the model. So another way to think about this is when you're looking at the raw features in a machine learning algorithm, you're looking at the properties associated with individual entities, like individual customers. When you're looking at the graph features, you're looking at how different entities or different customers are connected to each other. Are they friends with each other? Are they colleagues with each other, and so on? So this new set of information that you can glean from looking at the connections is what we want to add to the model to reduce development time, increase accuracy, and so on. And the nice thing is these connections between data entities can be captured very easily from data stored in database tables, as we will see later in the session. So let me start by a quick overview of the graph data model. We are all familiar with the graph data model. You have vertices, you have edges, and so on. So, and there are many different kinds of graphs. You have physical networks like road networks, railway networks, where you're trying to find the best route between 2 points and so on. There's also logical networks. So given any data set, you can identify logical connections between your data entities, like friend of is a logical connection. Whether John transferred money to Jean is a logical connection. And so what the graph data model we are talking about now is the property graph data model, which enables you to represent your data as a graph using vertices, edges, and properties for vertices and edges. So every vertex can have properties and every edge can have properties as well. And as I was saying, the nice thing about property graphs is, when you think about it, is that almost any data set can be represented as a graph. If you take the financial transactions example here, you can have user accounts as vertices, and every time there's a cash transfer between accounts, that becomes an edge. This seemingly simple graph model actually has powerful applications in the financial services industry to detect fraud and so on, as I'll share a few customer examples. So in any data set, you can have logical connections. You can represent that as a graph. So you can get new insights into your data. And here again, we have properties for the vertices and properties for these edges. The cash transfer would have a date and amount transferred as properties. So I talked a lot about connections between data entities. So graphs are really good at detecting connections and also more complex patterns. For example, cycles. This is again a very common operation in the financial services industry when they want to detect whether money moves around in a cycle. Like account A, transfer money to account B, transfer money to account C, and then to D, and then D transfers money back to A. Perhaps there's a money laundering operation going on. So by looking at the cash transfer operations as a graph, they're able to detect such cycles. Graphs are also good at detecting paths. Like when A transfer money to D, is there a path between them? Did A transfer money to D, but going to some intermediate account? Is there a path between accounts A and accounts D? So graphs are good at identifying that. And some of these can be converted into features that you can use in your machine learning algorithm. For example, the number of cycles that a user account is on might be an indication that this account is involved in fraudulent activity. So that's a numeric or scalar value that you can use in your feature vector. And graphs are also very good at identifying more complex patterns. And this is from our customer of ours, PaySafe. And here on this left, they're showing here that they have a source vertex, a destination vertex, lots of money being transferred between these vertices, but going through a lot of intermediate nodes. So this connection information is important. When they're looking for fraud, they want to see whether this pattern exists, going from one vertex to another, but going through a lot of intermediate vertices. So let's talk about some use cases that are particularly suited for using graphs and connection information you can get from graphs in your machine learning algorithm. So let's look at how you would detect malicious attacks. When you're browsing on the network, you want to see which are malicious attacks and so on. So there are any number of algorithms that do this. And typically the way to do this would be you have IP addresses, you have packets. So these are individual data entities. You can track what these do. You can say this IP address is sending this information, or when you access this IP address, you redirect it to go to some other website and so on. It's also very interesting to look at this as a graphlet, which is like a subgraph within the larger graph, where you're looking at all of these entities together. You're not just looking at the IP addresses individually, but you're saying this IP address talked with this IP address, and this was the packet flow between them. So you're looking at this as a graph with vertices and edges. And then you can, when you run graph algorithms on it, you can use algorithms like degree centrality, the out degree centrality, number of edges going out, number of edges coming in, page rank, eigenvector centrality, and so on, to get additional features associated with each of these vertices that you can use in your as part of your features in a machine learning algorithm to get more accuracy in predicting that this is a malicious attack. So you're not looking at each individual data entities, but looking at it as how they interact with each other in a graph representation. Healthcare, the use case here, of course, is that when someone comes in with a particular set of symptoms, you want to try and predict the diagnosis. So you have medications, you have lab tests, you have all of this information. You also have public information, such as the research that connects certain symptoms to certain diseases and so on. So all of this information that you have that you want to use to make a prediction for a new patient that's coming in. So when you model this data as a graph, you get some interesting new information that you can use in your prediction process. So you can create a graph from this because you can say that these are the symptoms connected to these diseases and so on. So it's fairly easy to see the connection between the data items. And then when you're making a prediction, like when you have this new admission come in, instead of looking only at the raw features for that particular patient, you can look up the graph and find patients similar to this patient by looking to see whether they're neighbors of this patient in the graph. That is, they're one hop away from this patient in the graph. Take the features of those patients as well, those entities as well, and use them in the prediction to get a more accurate prediction. So graphs in this way also can be combined with other features when it comes to the prediction phase. So in the financial transaction example here, and financial transaction industry is very aggressive in adopting graphs because they really want ways to identify fraud. So our customer PaySafe models their user accounts as vertices and edges, cash transfers as edges. And they've gotten all kinds of interesting insights like the anomalous patterns I was talking about earlier. They also now began adding more properties to the vertices, such as the device used, the IP addresses, and so on. And they began to identify patterns in the sense that, okay, these are the vertices that are using the same device. Or these are the vertices that are using the same device and the same IP address and so on. And the more connected a subgraph, the more suspicious they get. That there's something fraudulent going on. Like, why are all of these vertices using this same IP address or within the vicinity, or the IP addresses within the vicinity of each other? So they cluster the user accounts to get more insights into which are the tightly connected communities, and that to them is something that they had to investigate further. They also use graph algorithms like PageRank and eigenvalue and so on to determine money flow patterns. Like here, for example, you have 20 different accounts transferring money to this account, which makes one transfer to this other account. Or in this case, there's a single user getting money transfers from 50 different accounts. So these might be anomalous patterns that they want to investigate further. So they're using graphs extensively for this, and they have now begun to use graphs with machine learning. So what they're doing is they're saying, we are also using machine learning to identify fraud, and we want to combine the two. So when you're looking at a suspicious account, they want to see whether there's any kind of known fraudster within 2-hop distance from this graph, and the graph being the cash transfer graph. Or is this user a part of a community with other known fraudsters in it? So these are for them, to them, red flags that they want to investigate further. And they need to translate this vertex into features that can be included in the machine learning algorithm. And when they're able to do a good transfer of that, so that's what's known as vertex embedding, translate the information that these two nodes are connected to each other to something that you can consume in your feature vector, they're able to do better vector classification, find similar segments, have better prediction in terms of how predict what this user account is going to do, better classification, and overall improvement of their machine learning models. So these are very interesting use cases which really look at the connection between data items and leverage that or use that in their machine learning algorithms or applications. So now let's look at how you can do some of these things in an Oracle Autonomous Database. So first is an overview of the product itself. So you can store, manage, query, and analyze graphs in an Oracle Autonomous Database. And what we also provide is a highly scalable, specialized graph server that runs in a compute instance. So along with your autonomous database, you would provision a compute instance where you would run this graph server. We have a marketplace image for that. You would install this graph server, and this is highly scalable and specialized for graph processing because some of these graph algorithms can be compute intensive, like between centrality or PageRank can be compute intensive, and we want to be able to run these algorithms in milliseconds. So this in-memory graph server enables you to do that. So when you represent data as a graph, you need to query the graph, and that's the property graph query language. It's a SQL-like query language which has the ability to specify patterns. So you have the select and the from and the where clauses that you would expect in SQL, and also you have a match clause that helps you identify specific segments within your graph. We also have a pre-built, over 50 pre-built graph analysis algorithms. So you can run these algorithms without having to write your own algorithms. You can customize them if necessary, but if you just want to use what is available out of the box, it's very easy to run them in your Java application. And we have a visualization tool that I think I'm going to try and show you in a demo. So when you start, you would provision your autonomous database instance that stores your graph database. And then you would provision this compute instance where you would install from the OCI marketplace a graph server and client that would include the in-memory graph server, graph client, the Zeppelin interpreters, and so on. So creating graphs. I talked about storing graphs in the database, and it's easy to create graphs. So let's look a little bit about how exactly you would create graphs from data stored in relation tables. So here's a simple example with two tables. You have an accounts table, that's a list of account IDs, and then you have a transactions table that shows you when there was a cash transaction between two accounts. So what the data entities are the accounts, and what are individual data entities in your data naturally become vertices in your graph. So when you create the graph using the PGQL data definition language, DDL syntax, you can say create this graph, and this is my vertex table. And by that I mean every row in this table becomes a vertex in the graph, and the column values can become properties of the graph if I specify that. So I'm saying the properties for these vertices are going to be the account ID. And then the edge table comes from the transactions, and this is the source vertex, the destination vertex, and this is the property for that edge. So this is the amount transferred from this account to this account. So you're specifying the vertex table, the edge table, and so on. And you have to execute this. All you have to do is execute this PGQL statement, and then you're able to then create a graph. So, and you'll have a graph that looks something like this. You take all your cash transfer information and look at this graph, and we'll query this graph in a second. But before that, I want to just highlight that because I showed a simple example for creating a graph, I wanted to also highlight that you can create a graph for a more complex schema. So if you had the HR schema, that's part of the sample schema, which has more tables, so more types of vertices. Each row in each of these tables is likely to become a vertex. And foreign key relationships that become natural edges, and you can also add edges to them. So you would probably create vertices like this. You would have employees being a set of vertices, countries being a set of vertices, regions, and so on. And then you would have the edges that you would create based on the relationships between these tables. So I just wanted to quickly show that to again highlight that for any schema, you can probably create a graph. So now that we created this graph, we had this cash transfer graph. Let us see how we can query this graph. So here's an example of the PGQL query that I was talking about, when you have the select clause, and here's where you have the match clause. So everything in parentheses is a vertex, and everything in square brackets is an edge. So here I'm trying to determine cycles. I'm trying to say, is there a money flow from A to B, B to C, and C back to A? And here I'm saying I want to start with at ID 1 and see all the vertices that are connected to 1 with 1 to 6 hops. So basically I want to find everything that where I transferred money either through 1 hop or through 6 hops. So let's see whether I can quickly show some of that. So you see here, this is the basic query, which it is the equivalent of select star from tab, right? You're just selecting all the edges you have in the graph. So, and then we want to run some more interesting queries on it. So, okay, so now let's run some more interesting queries. By the way, I'm running all of this on the autonomous free tier instance. So now I'm saying, find me the first 10 cycles that are available in this graph, and you can see these are triangles where money is moving in these triangles with 3 hops. So let's run a different query here, the one which was looking from 1 to 6 hops. So looking at 1 to 6 hops, I'm starting with a node with ID 1. And I want to say, okay, find me all cash transfers that are 1 to 6 hops away from this particular vertex. So you see here 1, and then you have all of these other nodes that are connected to it between 1 and 6 hops. So I'll just run one more query here. So let's say you knew that there is a cycle that includes nodes 1 and nodes 259, and you want to find out the specific intermediate nodes here that form this cycle. So you can query this graph to find out the specific cycle, and you can see here that you have node 1, node 259, and the cycle that through which this money flows. So let me now go back to my slide deck here. So this example for query. So if when you're actually using graphs in machine learning applications, you probably embed the PTQL queries in your Java application, right? You are not likely to be manually running these queries and including features, but if you want to explore the graph, see what kind of connections you have, this tool is useful. And I also wanted to give you a flavor of what it is to run a graph query and visualize the results. So what I just showed you was our visualization tool runs from a browser. You type in your PTQL queries and you get back your results as a graph. So now the graph algorithms I talked about, I mentioned degree centrality algorithms, page rank, between a centrality, detecting communities, right? Strongly connected communities, communities that are connected to each other. There are many different algorithms that we have. So these are some of the over 50 algorithms that are available as part of the feed property graph feature. These can be run from a Java application. They can be run from Zeppelin Notebook. We have Zeppelin interpreters for the in-memory graph server. And we have a native Python client that is in our roadmap. And if you were to run this on Zeppelin, this would sort of look like this. You would take the analyst object and you run these different algorithms, page rank, between a centrality. So the between a centrality graph algorithm helps you identify nodes that are in most of the paths between other nodes. In other words, if you remove this node, your graph could become disconnected or more weakly connected. So that's another way of determining how important a vertex is in a graph. And this is SEC Kosarajo is a way to identify the connected components in a strongly connected components in a graph. So with that, let me now try to put this all together. So you have your data in tables in Autonomous Database, and you're planning on using Oracle Machine Learning Notebook to do your machine learning, but you want to see whether you have any connections in your data entities because you want to use that as part of your machine learning model creation. So you can create a graph, and as I showed you an example, you just run your PTQL statement to create a graph, load that into the in-memory graph server, and then write the results back into a table. So when you execute a PTQL statement in Java, you can just iterate through the results. It's just like running any kind of Java query, a SQL query in Java, and you just you can write the results back into a table, and then use these features in your machine learning algorithm. So basically, all your data is in your Autonomous Database. You just do this graph analysis and then start use that results of that in your machine learning algorithms. So now next to our roadmap. So I talked a lot about the new features that you can add for vertices in your graph, the vertices mapping to data entities, and they tend to be properties associated with a vertex, like a page rank value of a vertex. There's a lot of work being done now to include a graph pattern itself in your machine learning algorithms. So not just take a numeric property from a vertex, but to take the entire, like a subgraph or a graph pattern and include that in your machine learning algorithms. So including that is part of our roadmap. I'll talk about two of those algorithms. So in PG2Vec, you start from a vertex and you start doing random walks from one vertex to another. You have predefined length per walk, predefined number of walks per vertex, and then you concatenate the properties of the source and destination vertices as you go along. So when you use that in your machine learning algorithm, you're able to detect that this graph, or predict that this graph has the same pattern, or detect this graph has the same pattern as this pattern that I'm looking for that I trained my model on. And then GraphWise, which is built on GraphSAGE, and the Oracle Labs folks optimized it. So that is an algorithm that uses two graph convolutional layers. And these layers are looking at the neighbors in a graph to aggregate the values of vertices with aggregate the values of one vertex with the neighboring vertices, and then use that in the layers, and the rest of the layers are just going to be standard neural network layers. So include two graph layers in the standard neural network process. So the last item I want to mention as a roadmap is that we are also planning an autonomous graph database in the cloud, a cloud service, which is going to be a fully automated graph platform. Like I showed you how you can create a graph and load that into memory and so on. All of that will be fully automated. You can point and click and drag and drop and say, these are the tables I want to include in my graph. And a lot of the relationships will be automatically determined for you, that these are the potential edges you want in your graph to look at your data set as a graph. So for example, here you can say, I want to start modeling my graph. I want to, and then you can say that, okay, I want to look at the schema, I want to look at the tables in the schema, and I want to create a graph and so on. So just a couple of screenshots to show how we are automating the graph creation process to make it even easier. Let me summarize my statement by our customer, which says graphs and machine learning combination is powerful. And it really gives you the ability to include features generated by connections in a graph in your machine learning applications. So that, I think this is an exciting new area. Folks are looking for a way to get an edge into how they have built better models. And graphs give you one way to do that. I would like to acknowledge my colleagues, Richie from Orade Labs, Riota, my colleague in product management, and Gautam who helped me with the demo. And of course, the rest of the team. So with that, let me go to the Q&A slide and stop sharing for a second while we answer questions. So let me take a look at some of these questions. Okay, so one of the questions here is this something I can do today? Yes, you can. So I clearly separated out the roadmap, which is using algorithms that include graph patterns, and everything till the roadmap slide, everything I talked about can be done today. You can create, you can model your data as a graph. You can create graphs from your data. You can run graph algorithms. You can take the results, include that in machine learning algorithms and everything. So all of that can be done with products you're shipping today. And the examples I used just now are, I actually ran that demo on the autonomous database free tier. So it's something you can easily get started with. Oh, and that's also a next question that came up. Can I try this in the Oracle Cloud Always Free tier? You absolutely can. We do have a graph demo in the Live Labs section, in the Live Labs page. And so yes, you can definitely use that. The third question is, can the creation of a graph be automated? Yes, as long as for now, right now, you would have to sit down and think a little bit about what you want to be your edges and what you want to be your vertices. And once you do that, it's very easy to create a graph. And that exercise is helpful in helping you determine exactly how you want the graph to be connected, and what are the relationships you're looking for, like what connections are interesting to you. So I think it's a useful exercise to sit and look at the graph a little bit and think about how we want the graph model. But once you have an idea of the graph in your mind, that creating the graph itself is very simple and can be automated. And as I was saying, we have the Graph Cloud, the service, autonomous graph database coming up, which will make this process even simpler. So here's another question that I'm saying, are there use cases about recommendation systems with Oracle Graph Database? Yes. You can use the Oracle Graph feature with the Oracle Database for building recommendation systems. And in fact, we have an Ask Tom session that I think we did last month that focuses on product recommendation. So I would encourage you to go look at our Ask Tom landing page to take a look at that session, which is focused on recommendation systems. So what we do there is the edges there are, when a customer buys a product, that's an edge. And then you try to group customers by the products they buy, and then you try to predict whether somebody will belong to this cluster and buy a product and so on. So please take a look at this session. Another question is, what's the best option, autonomous database or autonomous graph database? So I don't think it's an either or. So you would use your autonomous database for a whole bunch of applications. And if you want to use graphs with any one of your applications, we have made it easy to create a graph model, made it easy to query the graph and analyze the graph and so on. So it's not either or. I would say your relational autonomous database is your core platform for your applications, and you can additionally include graph features by using the property graph feature of the Oracle Autonomous Database. Okay, another question is, in machine learning, the model needs to be trained. However, in the database case, it looks like it's to be assumed. Yes, the model does need to be trained, right? And if you look at the OML, Oracle Machine Learning examples, there will be examples on how you can train your model. And so that there's nothing different there, that the models has to be trained. And all I'm highlighting is that you can use graph features as part of your training process. So here's another question about what accuracy can we expect when you're using graph features in ML? So that's an interesting question. So it all depends on exactly, I guess, what you're doing and what your use case is. So when the data set has connections within the data, then you can probably expect to get improved accuracy when you are using this graph connections information in your data set. So it's hard to say that there's one accuracy that you have across all use cases. It really depends on the use case, depends on what you're trying to do. Like in the PaySafe example, they were saying that we were seeing a clear improvement when it came to using graphs with their machine learning algorithm. So it's hard to say what accuracy you can expect, but I can say that our customers are seeing improved accuracy depending on their use case. Another question here is GraphQL part of the autonomous database package? Yes, so we call that the property graph query language. We have made it as SQL-like as possible to make it easy for SQL developers to learn how to use this language. And by the way, you can run this property graph queries in the SQL CL client as well. You can run it embedded in your Java application, or you can run it using the interpreter we have for Zeppelin. So you can run it in a number of ways. And this is part of the property graph feature, and the property graph feature is part of autonomous database. So when you provision your autonomous database, when you install the graph server from the marketplace image, you have access to this. And just a note on languages, we are participating in the standard that will extend SQL to include graph queries. And we are aligning out the PGQL language as closely as possible to things that are emerging from the standard. Another question, do you have any online tutorials or demos to help me with this? Yes, we do have the Live Labs. So let me see how I can find the link here. Yes, we do have a Live Labs, a Graph Lab on the Live Labs infrastructure. So let me see, maybe I can post that here. I guess I'm posting it to folks on my panel, so maybe I'll try to post it to everyone here. So if you can go here and you can check out this Graph Lab, and feel free to reach out to us with any questions and so on. We would love to hear from you. And we do plan to keep adding more labs to that particular page. So one more question, I think we have time maybe for one more question. What graph algorithms make sense to identify vertex features to use in ML algorithms? So yeah, that's another interesting question. So any graph algorithms that tell you more about the vertex, like PageRank value, when you apply PageRank, it gives you the importance of that vertex, or in other words, how connected that vertex is. And it gives you that in like numeric form. So PageRank will return a value between 0 and 1, and higher the value, more connected or more important is this vertex in the graph. So that's a classic example. Degree centrality is how well connected a vertex is to the graph by looking at the number of edges that are connected to a vertex. So these are all the classic algorithms. And you can also do other things like how many cycles is this vertex on? and how many between the centrality. Again, that gives you a value that determines how many paths this value, this vertex is on. So any such algorithm that kind of gives you an idea of how connected the vertex is in the graph, or the relationship of this vertex to other vertices in the graph, are a candidate for using in ML algorithms. So once again, question recommendation systems, please do check our Ask Tom page. I think last month we did a session on recommendation systems. I recommend that you go and check out that session, and feel free to reach out to us when you have more questions. And last question, what ML algorithms are available to apply to graph analytics and database? So I think you can expand the feature vector with these graph features, and pretty much you can use this in a variety of machine learning algorithms. There's no real restriction there. I think it's a question of what machine learning algorithm really makes sense for your use case. So I think our time is up. So I'm going to go ahead and share what's coming next. Right, so we have great 2 new sessions coming up. So I hope you'll join us there. Thank you very much.